So today we're doing graphing with trigonometry, um, week 3 of trigonometry. So next week we have another week of trigonometry, and then it's the end of the year. So you guys can go and enjoy your summer after that. So trig 3 graphing, okay? I'm going to first talk about the general features of any graph and apply that, what we know, to sine and cosine graphs, tan and cotangent graphs. But we're mostly going to focus on sine and cosine graphs because that's usually what's relevant. Nothing else has that many applications. So we're just going to focus on that for now. Okay, so let's dive right in. So the general features of a graph. So for any graph, we have this thing that they like to show in school. It's like a times f b x minus h plus k. So if we have a function f of x, we can convert this. We can transform this function, right? Let's say this function looks like this on the graph. We can transform it based on what these numbers are. So the first one is a. What does a stand for? I think most of you should. This is just review mostly. If you already know this from algebra 1, but a is how stretchy it is in the vertical direction. So if a is really big, it's getting really stretchy. So if a was like 3, if I had 3 times f of x, so a is like what's multiplying by the whole function. So if it's 3 times f of x, then everything becomes a lot more stretchy. It becomes more elongated. And if it's a fraction, like 1/3 f of x, it gets more, it gets squeezed out. So okay, so that's what a does. B, on the other hand, is how stretchy in the horizontal direction. So let's take f of x again. So the key here with anything that's inside these parentheses is that it's opposite of what you expect it to be. So just like with 3 f of 3x, we would expect this to stretch it in the horizontal direction, but it doesn't. It's the opposite of what we expect. So f of 3x actually shrinks it down, so in the horizontal direction. Okay, this is f of 3x. So whatever's inside the parentheses, it's opposite of what we expect it to be. Okay, so f of 3x, we expect it to be stretched out, but it's actually being compressed. So f of 1/3 x, we expect it to be compressed, but it's actually being stretched out. So f of 1/3 x looks really stretchy in the horizontal direction. Same with whatever's going on with h. If I had f x plus 1, so h is what we call horizontal shift. We're just literally shifting the whole graph in the horizontal direction. Okay, so f of x plus 1, we would expect this to move to the right by 1. But no, it's actually moving to the left because whatever's in the parentheses, it's opposite of what we expect it to be. So if this was f of x plus 1 would be 1 to the left. Okay. F of x minus 1, that's 1 to the right. So it's the opposite of what we expected. Okay. And then for k, it's outside the parentheses. It is what we expect it to be. So k is vertical shift. And it is what we expect it to be. If it's positive, like f of x plus 1, it's moving up. It's what we expect since it's outside the parentheses. Okay. This was f of x plus 1 is moving up, and that's what we expect it to do. Okay. This should mostly be review for you guys, if you've done algebra 1, which I think you must have. So another thing is that if a and b are negative, what happens if that happens, right? If a is negative, you reflect the graph over the x-axis. You reflect in the vertical direction. So if this was f of x, negative f of x, I would reflect this whole graph over the x-axis. Something like that. Okay, and you can expect if b is negative, you reflect over the y-axis. Okay, so if this was f of x, and I wanted to find f of negative x, so b is the thing that's multiplying what's inside. F of negative x, it would be something like this. Like I reflected across the y-axis in the horizontal direction. Okay, that's it. Any questions here? So another thing to remember is that b is multiplying x minus h as a whole. So if you had f of 3x minus 3, you have to factor the b out first before you can determine what h is. Okay, this is not a shift of 3 to the right. No, you have to get rid of this 3. You got to factor out the b first. So 3x minus 1. And then now you know it's a horizontal shift by 1. Okay, so you have to factor out the b before you can get the shift. Okay. Okay, so I sent you guys a PDF with like 12 of these things. So if you have that in Notability or you print it out, you can use that. So I just want you guys to approximately plot the graph of y equals cosine x by plotting points. Okay, so just plot in values and then it will trace out some kind of graph. And I want you to graph that. Okay, so do it all the way to 4 pi. So from 0 to 4 pi, I want to have a graph within this domain. Okay, let's take 5 minutes to do this. Okay, so let's try to graph this. So we'll just start, right? So when x is 0, y is 1. Okay. So if we draw the unit circle, x is 0. So we're obviously doing radians here. So if x is 0, y is 1. You can observe that as x increases, y decreases until we get to 0 at pi over 2. So it's going to decrease until we get to pi over 2. And you can see that actually, first it decreases slowly because it's kind of going straight up. And then it tilts to the right, and then now it's going really fast this way. So it starts out decreasing slowly, and then it goes faster. And then right here is just the opposite. Starting from 0, it's going negative now. It's first decreasing very fast and decreases slowly all the way down to -1 for pi. Okay. Now from -1 to 0 again. So it's going to look like this from 0 to 2 pi. We're back where we started. Right? If we keep going, we're just going to keep going in the circle, right? So which means we're just going to take what we had originally, copy paste it, and just put it here. Right? Because we're still going around the same circle. There's nothing different about what we're doing. Right? So we can just copy paste what we have from 0 to 2 pi, and we can be sure that that's the same exact thing that's going to happen from 2 pi to 4 pi. And if we were to keep going, right, we're still going in the circle, right? We're going to go back to original at 4 pi. We can go again, and we'll get to 6 pi. So every 2 pi, we can draw this little U shape. It can keep going on and on forever. So that's the graph of y equals cosine x. Okay, so I'll give you a second to maybe draw this down in your notebook, wherever you're taking notes. So it starts out high and then it goes down, up, down, up, down, up. It's like a wave. Okay, we usually call this a wave, like a cosine wave. Okay, so that's what we describe this shape here. So it's at the top, it's like a hill and a valley. So this is a hill, this is a valley. It goes from the hill to the valley to the hill to the valley. Okay, so now let's do the same thing with sine x. Okay, this should not take that long after we did the first one, so I'll give you guys 3 minutes. So this one's really similar to the first one. Let's go back. Starting here, sine is 0. And then the graph really rapidly increases because if you imagine the dot moving here, it's going upwards really fast. But when it gets here, it reaches like a flat level. So the y value is not really increasing that much. So it's going to go all the way up to 1 by pi over 2. So it's going to increase fast initially and start to level off by pi over 2. So it's going to look like that. It's going to go back to 0 now, starting by moving slowly downwards. And then it quickens. So it's going to go like this. And now it goes from here to pi over 2. And as it does that, it goes from 0 to -1. And at first it does so really quickly, and then it kind of levels off. So, and then finally it goes from here all the way back to from -1 to 0 again. And it's going to start really slowly, and then it's going to get really faster as it gets there. Okay, now we know that since we're still going in the circle, we could just copy paste what's from 0 to 2 pi over and over again to produce the rest of the graph. So could it go like that? Okay, this is the sine wave. Okay, so you can see that it actually starts out at the midpoint, immediately goes up to the hill. The cosine, it started at the hill and started to go down. Cosine looks like this. So the sine, it starts at 0, the midpoint. It goes up initially. And it keeps going on a wave, on and on and on. Okay, and it goes one full cycle every 2 pi. So that's why we could copy paste 2 pi over and over again, because it's going in a circle, right? So every path from 0 to 2 pi is the same as the paths from 2 pi to 4 pi, 4 pi to 6 pi, and so on. Okay, so now we're going to look at the key features of a sine and cosine graph. So I'm going to just draw a sine graph. Just for the sake of it, like we could have chose cosine. So we have these things that tell us how to graph this graph, right? We could graph the standard sine of x, right? The standard sine of x, we can graph that. But now we can apply our transformations to turn the sine, we could stretch it, right? So how do we stretch it? Or we could compress it in the vertical direction, or we could like stretch it in the horizontal direction, right? So there are many different kinds of sine graphs we can produce from this original standard sine graph. So we're going to use the basic transformations that we discussed at the beginning of class today. So to define how we're going to stretch this. So first one is A. This is called the amplitude. So this is basically how high this graph goes. Okay, so this is the amplitude. For sine of x, we know the amplitude is 1. It's right here, 1 times sine x, right? So amplitude for sine of x, right? So that's the standard. This is the standard. If we apply any transformation to it, let's say we want the sine graph to be stretched 2 times as much, the amplitude automatically goes to 2 because it's the a, right? The a value in a times f of b x minus h. Okay. All right, so a is the amplitude. It tells us how high these peaks are from the midline. It's like the middle line where it's like symmetrical. Okay, so the amplitude is how high it goes, how high the peaks are relative to the midline. Okay, so that's basically it, right? Because the first one tells us how stretchy it is in the vertical direction. Okay, so if A is big, it gets really, really tall, basically meaning we're stretching it a lot. Right? Because the standard one, the base was 1, which means if we're going to stretch it, the amplitude goes up by a factor of a, but that means the amplitude gets to a because it started at 1 originally. So a times 1 is still a, right? So that's why the amplitude itself is the a value. It is the a value because the base was 1, which means if we multiply by the a value, the amplitude is automatically becomes the a value. So the amplitude is the a value. Okay, so that tells us how stretchy it is in the vertical direction. Next one is t. T is period. The period is the amount, is the range, is the distance that tells us one full cycle. Okay, and after that, it just repeats over and over again. So how long is one full cycle? That's the period. So the period is like the measured distance in the x direction. Okay, if the period is long, it means that one full cycle takes longer to complete, which means it's more stretchy in the horizontal direction. Right, so in this case, the period is longer. If you want the period to be shorter, the graph kind of compresses. Okay, so the period is the amount of time it takes for one full cycle. For sine of x, the base, like the basic function, this is the foundation, right? So for this one, the period is 2 pi. It cycles every 2 pi. Okay, so t is basically like b here in this thing. T determines how stretchy it is in the x direction. Okay, which means if the period is long, if the period is very large, it means b is very small. Right? If b is small, we know that means we're stretching because it's the opposite of what we expect it to be. Okay, so that's why t is in the denominator here. It's so that it matches our definition of b. If b is smaller, the graph is stretched. So the graph is stretched if t is larger, which means t has to be in the denominator. Okay, and we can see that for the base, t is 2 pi. So if we plug this in here, since it's 2 pi over t, 2 pi over 2 pi is 1, which means b is 1. So b is actually technically 2 pi over t. Okay, and that's how stretchy it is in the x direction. Okay, so we can see that for the base, t was 2 pi, so b was 1. Right, b has to be 1 for the base, for the foundation. So that's why we defined to have this extra 2 pi factor there. So it's not just 1 over t, because if it was just 1 over t, it would not be accurate in the case of the foundation. Because in the foundation, the period has to be 2 pi, which means, but in the foundation, the b is also 1, right? So how do we make that happen? We have to have this equation. So 2 pi over t, that is b. So we often replace b with this w symbol. So we could actually rewrite this equation as a sine wx. We just often replace the 2 pi over t with this w. It's actually called omega. It's a Greek letter omega. So that's just a replacement for b because we often use this. It's just a standard for our symbols. So omega is often a replacement for b. So omega is still equal to b or 2 pi over t. Okay, so that's the horizontal stretching or compressing. And finally, k. K is just really, really simple. K is the vertical shift, right? So this is sine of x. If k was 1, we just shift the graph up by 1 unit. Okay, that's simple enough. So that's it. So A is what controls the actual stretching in the vertical direction. And A is the amplitude. So A is how tall it is, how tall the peaks are. Okay, that's exactly the number. So if we had like y equals 3 sine x, the peaks are exactly 3 units high. Okay, and then 2 pi over t That's the B value, which determines how stretchy it is. And then, yeah, that's it. Any questions? So just applying what we know about the transformations to these sine and cosine functions. All right, we have 6 graphs here. 6 graphs, which means you should have space on your worksheet to graph all of them. So I'll give you guys, let's say 12 minutes. So 2 minutes per graph. I think that's pretty reasonable. So I'll let you do that. So for the sake of time, I'm going to start explaining these now. We have like 2 minutes left until 12 minutes, so I'm going to save some time for like a word problem that's going to appear. So first one. Well, we got to figure out what's the amplitude. Amplitude is 3, so that's how high the peaks are going to be. But also we have a vertical shift downward by 3. That means the midline, which is like the middle line, which everything oscillates around, is going to be right here. And now we're going to start with the cosine. Cosine starts at the peak, it goes down, it goes up, it goes down. So it starts at the peak, and the peak is 3. So where does the first peak exist? Well, since this is 3 down, and the 3 up is the peak, well, it starts at 0. So it goes down. And it looks like we don't have any change for a period. The period's still 2 pi, which means it hits the minimum. It means it hits the minimum at pi and goes back up to 2 pi. And then it just continues. So that's the graph of 3 cosine x minus 3. Okay. Next one, 4 sine of 2x. Graph this one. Well, amplitude is 4. It's a sine. And it looks like we do have a period change. So 2 pi over 2 pi over t. Remember, this is the b value, and the b value is 2 here. So t, if we solve this equation here, t should equal to pi. So every pi, it goes, remember the regular sine function, it does this in 2 pi. Now we want to do the same thing, up, down, back into the original in pi. So we're going to do it a lot faster. Okay, so that's basically what's happening here. So the period is now pi, and then we have an amplitude of 4, which means it hits the maximum of 4. So we're going to oscillate like this. So hit 4, come down, hit pi. Remember, it has to do a whole cycle in pi now, not 2 pi. It's thinner. It looks like that. Okay, so it's being compressed. So the period is now pi, so that's why we had this up, down, and back to original in pi. And everything after that is just the copy, repeat. Okay. Next one's a little tricky. How do we do this one? Well, you got to use, well, if you look at it closely, just look at it really closely, you will see that this looks like the Pythagorean identity. Isn't that right? That does. That is the Pythagorean identity. And we know that for whatever this always equals to 1. So the graph of this is just 1. It's just y equals 1. Right? So there's nothing too hard about this one, other than the fact that you had to realize this is the Pythagorean identity. So whatever it is has to equal 1 at all points. So yeah, this is that graph. Next one, amplitude of 4, but we have a translation. We have a horizontal shift now to the right by pi. Okay, so we're shifting the whole graph to the right by pi. So let's first draw in without the shift. Without the shift, it looks like this. Just a regular sine graph, except with amplitude of 4, right? So that's what it looks like without the shift. Now we have to shift it to the right by pi. Which means this goes here, this goes here. So it kind of looks like this now. Let me use a different color. It starts here. And I'll fill in the rest of this behind. If we look here, take away the black stuff, this is the new graph. So we've shifted it to the right by pi. Next one, we're just kind of applying everything we know here. First of all, we have an amplitude of 6. We also have a vertical shift by 2. So it means the midline is kind of like here. The period is 2 pi over t, and that equals 2 here. So t is pi. So the period is pi. We also have a shift of pi over 6 to the right. We'll figure out that shift later, but let's first graph what we know for now. So an amplitude of 6 within a period of pi. So it looks like this. And so we have, now we got to add in the shift, right? Pi over 6. We could just draw this, and pi over 6 kind of looks like this. So we're going to shift everything to the right by pi over 6. It's just going to kind of look like this now. All right, so, and so on. Okay, so we just take the graph without the shift, just shift it to the right. Okay, and finally, this one. This one's a little tricky. If you look closely here, I didn't tell you how to graph whatever happens if it's squared, right? We don't know that. So the trick here is to realize, let's first factor out a 2 sine squared x minus 1. If you're very, very careful, you will see, using your double angle identity, this is negative cosine of 2x. Okay, which means this is negative 2 cosine 2x. So this function is the same thing as that. We just need to graph negative 2 cosine of 2x. So first of all, the amplitude is 2, right? But it's negative. What does it mean if it's negative? We reflect it across the y. So the cosine usually has a peak initially, but since it's reflected now, it has a peak, has a valley initially. Okay, so let's graph this. Remember, first of all, amplitude is 2, which means it's oscillating around these 2 points. We have cosine 2x, which means the period. We've got to find what that is. 2 pi over t is 2. T is pi now. Okay, so if t is pi, do this real quick. We got to do the whole oscillation within pi. So since it's negative 2, we start at the valley. We go all the way up and we come back down within the range of pi. And we just keep oscillating like this and on and on and on. Okay, so we don't know how to graph sine squared x, but we do know how to graph cosine 2x. Right, so try to look for some of these transformations that you can do. So it doesn't seem like I have time to cover tangent and cotangent. How about this? I will graph this for you. Okay, so I won't let you try this yourself, but I will graph this for you. So what's the graph of tangent x? Remember, tangent is sine over cosine. Sine is the y value. Cosine is the x value, which means y over x. Slope. So tangent of x is the slope. So initially it's at 0. And then the slope increases until it goes really, really, really high into infinity. So it starts at 0, and at pi over 2, is here. It goes all the way into infinity. So it's like, goodbye. It's like an asymptote. If you've learned about these in algebra 1, this is an asymptote. So it goes all the way into infinity as it gets closer. Now over here, on the other side, it's really, really steep, but it's negative now. The slope is negative, which means it's starting out here. When you get to pi, it's back to 0. So, and now if we go to 3 pi over 2, another asymptote. So it looks like this. And then we can see that the pattern is emerging, so on like this. Tangent x is like these waves going up and up and up forever. Okay, so that's what tangent x looks like. Cotangent x. Well, remember, cotangent is the 1 over tangent. Okay, so let's first look at this. Initially, tangent is 0, which means cotangent is 1 over 0, which is infinity. So it's really, really high up. So the asymptote actually starts out at 0. It's really high up here. And as we move to pi over 2, tangent goes to infinity, which means cotangent goes to 0. So as we get to pi over 2, cotangent comes down, it goes to 0. We go back to pi, tangent turns into a negative. So right here, tangent, negative infinity, is kind of like negative 0, so it's crossing and now it goes down to pi. That pi tangent is 0 again, is actually -0 technically, and cotangent is -infinity. So have another asymptote. And you will see that if you keep graphing this, it kind of looks like this. That's the graph of cotangent. So basically, if you want to find these baseline graphs, you just need to graph them, plotting points. And then just like sine and cosine, apply the same transformations that you had if you have any other variations. Okay, I went a little bit over time, but that's all I have for today. So I'll see you guys next week. Bye.